Alright, so the goal of this video is to try to justify what the sum of consecutive squares is. So what's 1 plus 4 plus 9 plus 16 plus 25 ... What is the sum up to the nth perfect square? All right. After we finish this, I'm going to challenge you guys to figure out what the sum of the first n perfect cubes are. What is that? 1, 8, 27 ... And then theoretically, in doing that, you can also prove the sum of the first consecutive nth powers. So 3, 4, 5, whatever you want it to be. So the goal here in this video is just to do the sum of the first n consecutive perfect squares, but the idea will extend to larger powers. Let's go ahead and get started. So to do that, I want to look at some concrete examples of a linear, a quadratic, and a cubic function. So here are three different functions. 3x plus 5, that's our linear. Y equals x squared, that is our quadratic. And then we'll do y equals x cubed, that's our cubic. So what does this look like? All right, so let's plug some things in. We get 1. When you plug in 1, you get 3 plus 5, that's 8. When you plug in 2, you get 11. When you plug in 3, you get 14. When you plug in 4, you get 17. And when you plug in 5, you get 20. All right. Over here, when you plug in 1, you get 1. When you plug in 2, you get 4. When you plug in 3, you get, 9. When you plug in 4, you get 16. When you plug in 5, you get 25. Cool. All right. Over here, cube. All right. When you plug in 1, you get 1. When you plug in 2, you get 8. When you plug in 3, you get 27. When you plug in 4, you get 64. When you plug in 5, you get 125. And for clarity's sake, I'm going to plug in a 6. You get 216. All right, cool. So let's look at these things. All right. This may be the first time I've shown you this, or it may be past news, old news. But the difference between 8 and 11, that's 3. The difference between 11 and 14, that's 3. 3, 3, right? With linear functions, there is a constant difference, all right? All right, let's look at the difference between outputs of a quadratic, all right? The difference here is 3, all right? The difference here is, 5, all right? The difference here is 7. The difference here is 9. There is no constant difference here, but if you take it one step out, you get 2, 2, 2. All right? So we call this the second difference. And the second difference in a quadratic will always be constant. All right? How about a cubic? All right? We have 7. Here we have 19. Here we have 37. Here we have 61, and here we have a 91. All right, this is not linear, but let's take it one step further. All right, we have 12 here. Oh, going off the page, sorry. All right, we have 18 here. We have 24 here. And we have, what is that going to be? 30 there. Look at that. All right. 6, 6, 6. There's a constant difference. There's a third difference that I wish I had room for. The third difference is constant in a cubic. All right, that's going to be important. The third difference in a cubic is constant. Here it is 6. You might be able to guess what how far you need to go out for a quartic or a quintic function. Right? In a quartic, the fourth difference is going to be constant. In a quintic, the fifth difference is going to be constant. So how does that help us here? Well, let's look at the following. All right, let's start by let's sum up these differences. So we have 91. We have 61. We have 37. We have 19. And we have 7. All right. And those are the differences between successive cubes. So 91, Let's jump back here real quick. 91 is the difference between 6 cubed and 5 cubed. So I'm going to go ahead and write it that way. 6 cubed minus 5 cubed, all right? All right? 61 is the difference between 5 cubed and 4 cubed. 37 is the difference between 4 cubed, 64, and 3 cubed, 27. 19 is the difference between 3 cubed and 2 cubed, all right, 27 and 8. And 7 is the difference between, what is that going to be? 2 cubed, 8 minus 1 cubed, 1. Cool. All right, so these are equal, all right? And something beautiful happens. We call it telescoping, all right? Just like an old-fashioned telescope will collapse on itself, this thing is about to collapse on itself, all right? Negative 5 cubed plus 5 cubed, that's 0. Negative 4 cubed plus 4 cubed, that's 0. 0. 0. All right? This thing is left to become 6 cubed minus 1 cubed. Or in other words, 216 minus 1, or 215. This gives us the insight that we need, because what is this thing? All right, this is the sum of some quadratic function. Look, those numbers, 7, 19, 37, 61, 91, right? They have a second difference that is constant. They have a first difference that is linear. 7, 19, 37, 61, 91, that is like this example. There's second difference constant. It is a quadratic function. So I jump back. 91 plus 61 plus 37 plus 19 plus 7, right? We are summing a quadratic. This may be useful to us if we want to sum up consecutive perfect squares, which are quadratic in nature. So let's do this thing. All right. I'm going to look at the difference of successive cubes of arbitrary value a. So a cubed, a minus 1 cubed. What is this thing? This thing is, well, a cubed minus, this is going to be Pascal's triangle. We're going to have a cubed minus 3a squared plus 3a minus 1. Cool. And then we are going, if we look at, if we simplify this thing, we get the a cubed goes away, the negative carries over, and we get 3a squared minus 3a plus 1. All right, that is the difference of successive cubes. Let's go ahead and use it. So let's add up n cubed minus n minus 1 cubed. All right, what is that? That's just 3n squared minus 3n plus 1. All right, how about n minus 1 cubed minus n minus 2 cubed? That's just going to be 3n minus 1 squared minus 3n minus 1 plus 1. And let's go ahead and do the next one. N minus 2 cubed minus n minus 3 cubed. That's going to be 3n minus 2 squared minus 3n minus 2 plus 1. And then if I just keep doing this, I get to n minus 1 minus cubed minus n minus n cubed. And that ends up being 3 times n minus 1 squared minus 3 times n minus 1, not squared, plus 1. And let me go ahead to the next page and add all these things up. All right, so we have this thing here. What happens when I add them up? So if I add up the left-hand side of this these sets of equations, keep in mind there's all the way from n minus 3 to n minus 1. These are going to go away. These are going to go away. And these are going to go away. And these are going to go away. And I'm going to be left with, this is just 0, I'm going to be left with n cubed on the left-hand side. All right, and this is where the magic happens. What's 1 plus 1 plus 1 plus n times? Because there's n of these equations. All right, that's just n. All right, what is 3n plus 3n minus 1 plus 3n minus 2 plus 3n minus n minus 1? That's just 3 times 1 plus 2 plus all the way up to n. All right, and there's a minus there. Right, we're summing up 1, n minus 1 is 1, all the way up to n. So 1 plus 2 plus all the way up to n is this. We know what that is. Let's actually get it real quick. All right, that is n times n plus 1 over 2. We had previously figured out the sum of consecutive integers. All right, and then what is this? Look at that. All right, we have 3, but this is exactly what we want. We have 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. We have the sum from 1 to n of I squared. That is the thing we're trying to figure out. And guess what? We now can find a solution. So this is 3. I'm just going to write I squared. I'm going to be a little bit lazy here. But we want this sum. We know what n is. We're going up to the nth perfect square. We just need to solve for for the sum of I squared. So let's go ahead and do that. We have n cubed is equal to 3 times the sum of the consecutive squares minus 3 times, what is it, n times n plus 1 all over 2 plus n. So we just need to solve for the sum of I squared. So that is, and this time I won't be lazy, I'll add the 1 and I'll add the n. That is, we have negative 3n times n plus 1 all over 2 plus n minus n cubed. Oh, my bad. There should be a minus here, which kind of changes things. All right, so actually let me go ahead and rewrite that. We have, I'm going to move everything to the, so we do have a divided by 3, but I'm going to move everything to the left-hand side except for the I squared, so we're going to have an n cubed plus 3 times n plus 1 all over 2 minus n. There we go. All right, cool. Let's clean this thing up and hopefully get a nice answer. We're going to get a 2n cubed plus 3 times n plus 1 minus 2n all over 6. Right, because the 3 and the 2 combine. This needs a 2 to become a 6 on the bottom. Yep. And then if we move things around, well, if we distribute, we're going to get 2n cubed plus 3n squared plus 3n minus 2n. And then we can factor out an n. So n divided by 6, 2n squared plus 3n. What is that going to be? Plus n. Or sorry, plus 3, because we factored out the n. And then this thing factors, I believe, right? Yeah. N times 2n plus 1 times n plus 1 all over 6. Yeah, there we go. Nice. Cool. And that is the sum of consecutive perfect squares. All right, up to n. And I will leave it for you guys to figure out what is the sum of consecutive cubes. All right, the idea is very similar. All right, but we're going to need to know the difference between consecutive what would it be, fourth powers, and that'll help us generate a formula for the consecutive cubics. It requires you to know this. So there's a little bit of recursive thinking happening here. All right, but I'll leave that for you guys, the sum of consecutive cubes. All right, so there it is. There's your formula for sum of consecutive squares, and I will close out there. Have a good one, guys. See you next time.